Dear students, welcome back to this NPTEL online course on analog electronic circuits. Myself Pradeep Mandal from ENEC department of IIT Kharagpur. Today, we are going to continue the frequency response of common emitter and common source amplifier, and so it is primarily whatever the remaining topic it was there, we are going to cover today, and we will be mainly focusing on common emitter amplifier. So, in the previous day we have discussed about common emitter amplifier with fixed bias, and today we are going to discuss more about the self biased common emitter amplifier. So, what we have today, the overall plan, as I said that in the previous day we have discussed about the frequency response of CE amplifier, for which we have detailed discussion about RC and CR circuit, and then we have discussed about the common source amplifier, particularly with circuit analysis. Numerical portion it was not covered. So, today we are going to discuss numerical examples of common source amplifier. Likewise, for common emitter amplifier, as I said that for fixed bias we have covered. So, circuit analysis portion it was covered before, and today we will be discussing about some numerical examples. But before that we are going to discuss about the frequency response of common emitter amplifier with self bias arrangement. So, we are going to start with the common emitter amplifier with self biased and its corresponding circuit analysis, and later on of course, we will be going to discuss about numerical examples. From these numerical examples, we will get an idea that how to select the value of different capacitive components in the circuit. In fact, that will help us some design guidelines. In other words, in if say lower cutoff frequency and upper cutoff frequency is given to us, then how do we find that the coupling capacitor and what may be the possible load capacitance. Okay. So, again we are, since we are going to start from the previous topic where we have left. So, we need to just recapitulate some part of it, particularly the RC circuit and CR circuit analysis, which it has been deployed for fixed bias circuit, and then we will be moving to the common emitter amplifier with self bias. So, in the previous day what we have discussed, it is in case if we have say common any amplifier which is having say preceded CR circuit and then followed by the RC circuit, then the corresponding model of the circuit it is given here. And what we said is that this portion is the amplifier part, and on the other hand this portion, the C and R, they are forming the CR circuit, and then on the other side we do have this R and then C2, R2 and C2, it is forming the RC circuit. And what we said is to get the overall frequency response starting from the primary input to the primary output, what we have done is that we obtain the frequency response from this point to this point, and then from this point to this point, like V1 to V2, and then from V2 to VO. So, the overall frequency response it is having three parts. One is the frequency response of the CR part, and then frequency response of the main amplifier part, and then followed by frequency response of the RC circuit. And as we have you may recall that the first part, it is CR circuit frequency response, it is having 1 0 at 0 frequency, and then 1 pole at 1 by R 1 C 1. So, its transfer function it is given here. The middle portion it is having a voltage gain of A naught. So, A naught it is given here, and then the RC circuit on the other hand, its frequency response it is 1 by 1 plus S R 2 C 2. This is also having a pole at 1 by R 2 C 2. So, the frequency response what you obtained it is this part, it was giving us low pass high pass characteristic, and this value it was 0. I should say let me redraw here. So, this portion it was having low pass characteristic, high pass characteristic, having a cutoff frequency it is 1 by R 1 C 1. The middle portion on the other hand it was having constant gain defined by whatever this A naught, and then the RC part it is having a pole and its behavior it was a low pass kind of behavior, and combining the high pass, low pass, and then all pass, it was giving us the frequency response of the entire system. And note that the upper cutoff frequency of course, here it is 1 by R 2 C 2. So, overall frequency response we are obtaining is it was like this. So, this we have discussed in the previous class, and we are going to use the same model for CE amplifier having emitter degenerator, namely it is referred as cell biased CE amplifier. Now, again just for slight recapitulation, in case if you recall the fixed bias circuit, where this is the circuit diagram given here, which is having coupling capacitor here C 1 and C 2 signal coupling capacitor, and then we have drawn the small signal equivalent circuit of the amplifier, which is basically the core part, and then we have translated this circuit into this form, namely the input resistance of the core part R in, it is it was giving us say R 1, and then C 1 it is the coupling capacitor, signal coupling capacitor. On the other hand, output side we are having output resistance of this circuit, which is equals to R c, and R in it was R b in parallel with R pi, and then it was having the gain, which it was minus G m into R c. So, this circuit frequency response of this circuit it was obtained by considering its small signal equivalent circuit, and then further to further from this it has been mapped onto this generalized CR amplifier RC circuit, and then we obtain the corresponding frequency response of the CE amplifier. Now, let us so that is what we have discussed in the previous day. Now, we are going to discuss about CE amplifier having cell biased arrangement. So, you may recall that in the cell biased circuit we do have the emitter resistor and So, and also the at the base we do have R1 and R2 from this VCC to generate one DC voltage here, and then of course, the signal it was coming here through this signal coupling capacitor C1. At the output we do have the C2. Now, this circuit of course, if we consider the core portion and if we consider its small signal equivalent circuit, it is given here. So, this is the small signal equivalent circuit coming from the CE part. And if you again if you may recall that the overall frequency response V out by V in Laplace domain, it is having basically three parts. One is the C1 and then input resistance of the amplifier, that CR part, and then this amplifier part, and this is the RC part, which is coming from output resistance, which is RC, and these two capacitors, they are coming in series, and equivalently normally C2 it is much higher than CL. So, we can say that this series connection, it is giving us with this condition, it is giving us the net capacitance is CL. So, the frequency response of this part, it is similar to the previous case, namely the CE amplifier with fixed bias. We need not to repeat say this part and this part, rather we will be giving a focus on the middle portion, or you may say that the core portion. So, let us see what is the analysis of this core portion, and out of this what we are looking for, it is the voltage gain, whatever AV, and then R in and then R out. So, let us now go in detail into this circuit, and to get these parameters, so what we have to do, let we consider this signal, it is directly given to this point, and then we like to see what is the corresponding output you are obtaining, and if we take the ratio of the two, then that gives us the voltage gain AV. And on the other hand, if you stimulate this circuit and then if you observe the corresponding current, and then if you take the ratio, that will be giving us the input resistance. So, likewise for the output also, in this case of course, output resistance is straightforward to say that RC RO is equal to RC, but these two parts are a bit involved. So, let us go in detail of this core portion, and let we derive the expression of the AV part. Yes, so this is the core part of the circuit, and as I said that the signal we are directly feeding here at the input, and the output you are observing at this point. Now, what we are doing, that input we are giving at the base node and with respect to ground, but then emitter of the transistor, it is not connected to ground, rather it is connected to ground through this RE. As a result, this Vs and Vv, they are not equal, but of course, they are related. So, let us try to see how they are related. It may be noted that since Vs we are directly giving here, so irrespective of this R1 and R2, we are getting the signal at this point same as this Vs. So, I should say that the signal coming here, it is Vs, and out of this Vs we do have Vb part, and also we do have some additional drop here. So, what is this drop? And this drop with respect to ground, we may call this is Ve. So, the Ve equals to this Re multiplied by the current, and there are two parts of the current flowing through this RE. One is IC, which is GM into VBE, and then another one it is VBE divided by R pi, VBE divided by R pi. So, these two together it is giving us the emitter voltage here. On the other hand, the Vs, the total voltage here, which is equals to VE plus VBE. So, we can say that this Vs equals to, now we do have VBE here, and what we have it is VBE, we can take it out. So, we do have RE multiplied by GM plus 1 by R pi plus 1. So, this gives us the relationship between VBE and Vs. So, VBE equals to Vs divided by 1 plus RE multiplied by GM plus 1 by R pi. And if you see here, this R pi, it is equals to beta divided by GM. So, if I put that expression of this R pi here, what I will be getting here, it is I will be getting GM here and then divided by beta. So, that gives us Vs divided by 1 plus GM into RE multiplied by 1 plus beta divided by beta. Typically, we consider that this beta is much higher than 1. So, we can approximate this part is equal to 1. So, we can say that this is Vs divided by 1 plus GM into RE. So, that is the VB. Now, V out, on the other hand, V out, this is RC multiplied by this IC with a minus sign, and IC equals to GM into VBE. And then if I put the expression of VBE here, so this is the VBE expression. So, that gives us V out by Vs equals to minus GM into RC divided by 1 plus GM into RE. Okay. So, that gives us the gain of the circuit, which means that the mid frequency gain, it is basically it is coming from here. So, that is what we have written here, the gain is given here. On the other hand, the input resistance, if I see the circuit and if I look into this port and if I want to know what will be the input resistance we do have R1 in parallel with R2, sorry this will be R2, and then parallel with whatever the resistance it is coming from this circuit. Earlier we have discussed that the resistance looking into this circuit is R pi in series with this emitter resistor multiplied by 1 plus beta. Okay. Why beta? 1 plus beta, that is because in case if we are stimulating this circuit with a current IB, then current flowing through this collector, it is beta times that IB. So, the total current flowing here, it is 1 plus beta into IB. As a result, the drop across this RE, it will be IB multiplied by 1 plus beta into RE. So, if I take the ratio of the voltage here to here and then I b, which gives us the input resistance of this circuit. So, there we got this what you say that V b divided by I b equals to R pi plus R e into 1 plus beta. In fact, this is what the resistance it is coming here. So, the total resistance is R 1 parallel R 2 and then in parallel with whatever the resistance we do have. So, if you see here, that is the expression we are giving here. So, to summarize, so what we are obtaining here, it is this circuit. This circuit is having voltage gain of G m into R c divided by 1 plus G m into R e, and then input resistance it is R 1 parallel R 2 and then R pi plus R e into 1 plus beta. And this part depending on the value of this R e, we may approximate that this may be given by R c by R e. Likewise, here we can see that R 1 parallel R 2 that dominates over this resistance. So, the input resistance may be like this. And on the other hand, the output resistance, looking into the output port, what we do get is that R o equals to simply R c. So, this is also we have done before in some of our lecture, but in case if you have forgotten, probably if you see this circuit, since this portion it is ideal current, and if you look into this circuit and if you try to see what is the resistance of this entire circuit, it will be having only R c left behind. So, as a result, the output resistance it is R c, input resistance is practically R 1 parallel R 2, and then input on the other hand, the not input, the voltage gain, it is minus G m into R c divided by 1 plus G m into R e. Okay. So, yeah. So, what we said here, it is this should be R 2, and in addition to that R o equals to R c. So, so these informations, so these three expressions, basically the information about the core CE amplifier we are going to use to get the frequency response of this entire circuit. So, then if you see what will be the overall frequency response. Now, as we said that this is the small signal circuit where the core portion we have discussed just now, and what we have obtained that the gain here, the amplifier gain here, it is G m into R c divided by 1 plus G m into R e with a minus sign. So, this is the gain A naught, and input resistance on the other hand, it is R 1 parallel R 2 that dominates, R 1 parallel R 2, and on the other hand the output resistance it is equals to R c. So, to get the frequency response of this CE amplifier with the emitter degenerator, what we can do here, it is if you consider the first part, this part, and as we have said that the frequency response of that, it is having high pass nature, and the cutoff frequency here it is 1 by C 1 and then R 1 parallel R 2, assuming that frequency we are talking about radian per second. So, this is basically V 1 by V in decibel, That means, we have to take log of this ratio and then we have to multiply with 20. So, its frequency response of the CR circuit is given here, and then middle portion it is so the middle portion it is basically the amplifier part, which is having good gain, and the gain here it is coming from this Gm into Rc divided by 1 plus Gm into Re. May not be very high, of course, we have to convert in dB scale. So, and the frequency it is radian per second, and then the right part, the Rc part, it will be similar to the previous case. It is having the low pass nature, and its cutoff frequency it is 1 by Rc into Cl. Of course, we are assuming that this Cl it is much smaller than C2. So, that is the assumption. So, we are assuming that C2 it is much higher than Cl. So, if I combine now these three graphs together, so what we can get, that frequency response will be getting something like this. Right, and the lower cutoff frequency it is coming from here, and the upper cutoff frequency it is coming from here, and mid frequency gain it is obtained from here. So, here again it is very similar to whatever we have seen for CE amplifier, in fact, for common source amplifier also. But one thing I must say, that because we do have 1 plus Gm into Re in the denominator, the corresponding gain which is, you can say that this is Rc divided by Re, all practical purposes. Magnitude wise it is very small compared to Gm into Rc, that CE amplifier with fixed bias. And then what we have done is that we, to get back the gain, we have suggested to use bypass capacitor called CE to bypass these Re, and then in the frequency response it will be definitely it will be having some impact. So, what we are expecting here is that this CE part it will be here, and intuitively what we said is that in the mid frequency range, this CE it may be completely bypassing this Re, making this is AC ground, and hence the VBE it is equal to Vs, the primary input. And as a result, we said that the gain, instead of having this denominator in the denominator 1 plus Gm into Re, if CE it is bypassing it. So, this portion it will be 0. As a result, the gain we can get higher. That is what we said by intuition, but of course, depending on the value of the CE, when we will be getting this gain, the high gain with respect to Rc by Re, that may vary. So, depending on the value of the CE and probably the effective resistance at this node, there will be some cutoff frequency, or rather I should say the CE will be having direct influence on the frequency response. It cannot go directly here. We prefer to have a smooth gain, but if we are arbitrarily selecting this CE, then we may not get this frequency response. So, what you can do now, let we look into the frequency response of this CE amplifier having Re and C together, and let us try to see what is the corresponding frequency response. Yes. So, this is the circuit I was referring to. instead of RE, now we do have RE and CE together. And if you look into the core CE amplifier, which is of course, it is a different part compared to the previous case. So, let we focus on this. In fact, if you go back and if you see the previous circuit, sorry. Yeah. So, if you see here this part it is not having the CE part, but then its gain expression we can see that this RE it is directly coming there. So, whatever the analysis we have done for this circuit, similar kind of analysis we can do by considering this CE in parallel with RE. So, try to remember that what are the things you have done, or at least this is the expression of the voltage gain. So, the same voltage gain or similar kind of expression will be getting in case if this RE it is shunted by CE. So, what will be yes. So, from that previous analysis what we can say that the voltage gain namely V out by Vs, it can be written as minus Gm into Rc divided by 1 plus Gm into Rc in parallel with Ce and its corresponding Laplace domain transfer function. Sorry, this is Re in parallel with 1 by S into Ce. Of course, now we are talking about Laplace domain. So, I should use different symbol for this one. I should say rather V out S divided by V in S in Laplace domain instead of the time domain. And then what we can do that we can simplify this expression, and then we can see that it will be having additional pole 0 combination. So, let me take a short break and then we will start from here.